the first page of notes, which is why we didn't get very far. Of was important from our homework questions yesterday. Of, not multiply, but then in 1.9, didn't we have something new? F inverse, not f to the power of, right? Very different, very different, very different. So f inverse, not f to a power. And then Jordan brought up the whole cosine inversey thing about how in your calculators with second sine, second cosine, second tangent, it's inverse, not reciprocal. Can you guys grab out a calculator? At least one per group. There should be at least one calculator per group. Grab out one. Oh, poor Wesley. I'm going to have Wesley collaborate with Chris and Priscilla today because Lauren's gone. One calculator per group. Go ahead in turn so you can see the window of whoever has a calculator. I want you guys to do the following really quickly, just for a quick exploration. In your calculator, I want you guys to, just to prove a point, the difference between inverse and reciprocal. Can you guys go ahead and do tangent inverse? Real quick, be in degree mode. Be in degree mode. Most of your calculators are probably naturally in radian. Be in degree just because our brains work better in degrees, and we're not doing review of radians right now. Okay, do tangent inverse of... let's do 1. Tangent inverse of 1. And then I also want you in another operation to do 1 divided by tangent of 1. So tangent inverse of 1 and then 1 divided by tangent of 1. Does that make sense? Okay. Everybody peek at the calculator though. So what's the answers? Are they the same? No? So inverse doesn't mean reciprocal? Now can you do the entire tangent of 1 to the negative 1? Do the entire, like put a big old parenthesis around tangent of 1. Then do to the negative 1 power. So far you've done tangent inverse of 1. Then you're doing 1 divided by tangent of 1. And then what did I say to do next? How are you guys doing that? Okay. I didn't say that one. Do you remember what I said? Yeah, tangent of 1 to the... Which ones match? The second and the third one. So is the negative 1 power, is that a thing? Like, is it a reciprocal?
Yes.
Yeah, it's a thing. It totally works. But what did I do to raise that tangent of 1 to the negative 1 power? I put the whole thing in parentheses. So I raised the whole function. That's this, raising a whole function to a power. So raising a whole function to a negative 1 is the same as doing 1 over. So what was so different in what I did up here? Who is this again? Tangent inverse. So what's second sign? No. What's second sign? This little guy right here. Sine inverse. What's second cosine? Cosine inverse. What's second tangent? So how do you do cotangent? You have to do 1 over. How do you do cosecant? You have to do 1 over sine. How do you do secant? 1 over, or do the entire thing to the negative 1. So the difference between inverse and reciprocal is huge, okay? So can you do cotangent or secant or cosecant with the second button? No. No, you have to use 1 divided by or the whole thing to the negative 1. Long story short, I know we're not doing trig right now, but these are not the same thing. So coming back, whenever you see a little negative 1 in a power, in a function notation, whether it's f inverse or tangent inverse or what's another one? Log inverse, that's just awkward. You never see that one because we would rather go to exponential than do logarithms with an inverse. But every now and then, especially with trig and with like function notation, you'll see my mouse is right in the way. Excuse me, buddy, move over. Okay. Okay. Or if you see what I was saying, function notation, that's an inverse, not a negative 1 power. Okay? So with that, we were talking about inverses. And I was saying inverses, an original and an inverse, what's their relationship with each other? They're their own undoing. There's life lessons to that. But If you plug one function into another and everything's undone, yesterday, what was I saying? Addition, subtraction, multiplication, division, powers, roots, everything's undone but x, they're inverses. And you would also be able to plug the original into the inverse or the first into the second, and the same exact thing should happen. What happens when you take a composition of a function with its inverse, everything's undone. Now, at the very end of yesterday, we were talking about how to solve, just to try to get some of you guys into homework a little bit farther than you would have been able to go otherwise, with a whole review of switch x and y, solve for y. But what was the very first thing I did before I even switched my x and y and solved for y? Do you remember yesterday? What was the first thing I did? Set it equal to y. There wasn't a y to begin with, and some people will get confused by that. So you have to think of f of x as really y, then switch x and y, then solve for y. But what was the very last thing I did? Why did I write this? Notation, because when you solve for the y, he's not the original. He's very, 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 very different. He's the inverse. Did you guys already write this? You did, huh? Let's think through this. If you switch the x and y's, what's going to happen to the domain and range? What do you think? Yeah. Because all the x's of the f just became the what? If you switch it, all the x's of the f would become the y's of the inverse. So if it's the y's of the inverse, then this is going to be the range of f inverse. And then similarly, well, all the y's of the original are going to become what of the inverse? Yeah, the x's are the domain. Good. So since we have that whole switching x and y's thingamabob, the domain becomes the range, the domain of the original, range of the inverse. Range of the original becomes the domain. All of them switch, which means each of their individual points switch too, and we'll have to see that in a second. But let me try to illustrate this page really quickly before we move on, unless there's an example ready. I don't like that one. Let's use this example instead. We just found the inverse for this guy, 3x minus 1, right? So how could you test, I'll say test or verify. Test or verify. Taking this example that we just did, how are we going to test or verify that f and g are inverses? So I called this f inverse, but technically all I know without testing, unless I'm super, super, super confident of my work, all I know without testing is that, I don't know, here's another function and I'm pretty sure he's the inverse, so I called him f inverse. But how could we test and make sure? I want to illustrate the whole undoing idea. Sounds pretty dramatic, like, oh, it's its own undoing. Or the inverse is the original's undoing. But how would we test? Guys, look in your box right up in your notes. What am I supposed to do to test the two and make sure that they work? F of g, and what's that called, the whole putting in? Close, not combination. Yeah, louder. Composition. Composition. So combination is adding, subtracting, multiplying, dividing. Composition is plugging in. So we got to plug in. Who do you want to plug into who? Let's do f of g. That one's pretty basic, right? All right, I'm talking too much and you guys are just sitting too much, so I'm just going to go ahead and be your slave. I'm going to do whatever you tell me to do. Let's do this. How do I do f of g? Pretend I'm a really dumb servant and I have no idea what you mean by plug in. Pretend I'm really, really dumb. I don't know where to plug it in. Some kids would do that on a test. Some of you guys might do that on a test. Come on, you got to be specific. He's doing a good job. Someone help Matthew. Something's wrong. Help each other out. Help each other out. I know, it was messy. I totally agree. But someone knew that it was a 1. Okay.
And then write +1, -1, and then put a slash through both of those.
Pause. Why did I write a 0? I'm totally wrong. Why did I write a 0? You guys are using the word... You're using the word cancel. Cancel is equaling 0. 5 minus 5, negative 4 plus 4. Canceling means going to 0. What's the technical word for what this is? Slash. Be a good Halloween movie. Reducing. Call it reduce instead of slash. Anyway, reducing. Reducing goes to 1. And then you could say 1 times x plus 1 is x. Where'd the x go? There we go. X plus 1 minus 1 is x, right? Is that better? Okay. That's it? You're welcome. Anyway, so what happened? F was G's undoing, or was G F's undoing? Either way, everything was undone. What? The times 3 and the minus 1. What was it undone by? The divided by 3 and the plus 1, but in the right order. What would happen if we went the other way? G of F of X? Everything gets undone again, except for what are you left with at the end every time? Got it. Check. Dun, 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 dun. Whew, that was rough. Okay. Why did I have you skip this example? How nice and easy is it? Why? You don't have to write it down. Just walk me through it because it's so quick. Unless you want to write it down. Walk me through real quick. How do we find the inverse? 6y. Who is y? Okay. So then switch y and x and we get... How would we check? We did that last time. Let's go the other direction this time. Plug 4x into where? I know, it was that easy, right? No wonder I had to skip it. Dun, 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 dun. Division gets undone by multiplication. Multiplication gets undone by division. Addition gets undone by subtraction, etc. Were there harder ones in homework? Give me an example. What's a nice hard one? The 20s? Yeah, this is where it gets a little beastly. Yeah, 23 wasn't, he was a lot like the one we just did, huh, with the 3x. Down here somewhere? Yeah, it's weird, right? But you figured it out? And then it did flip, flip, and you're like, oh, it is x. Anything else complicated? Anything down here? Nobody got stuck on something around here? I thought there was. I was not that mean to you? Oh. Yeah, someone could pull out their homework spiral. Maybe I had one down here. Oh, I bet I had one down here instead. Okay, that's okay. We'll keep going because we have to get to the end of notes to get to the latter part of homework. That's the right way of saying that, right? Okay, here we go. Zoop, zoop. Graphically. We didn't get to this yesterday. Yeah, graphically. Inverse functions are reflections across a certain line. And if you guys look down below, and if you look at how it's labeled, as you draw it, you see that there's a gray f of x, there's a black f inverse of x. And is there symmetry? Well, I guess I shouldn't use the word symmetry because symmetry means like one graph has it all. These are two different graphs put together. It looks like there's symmetry. Technically, we'd say one is the reflection of the other. But is it reflection across the x-axis? No. Y-axis? Origin? No. But what is it across?
Y equals x.
Got it. What's the name of that line from parent functions? Y equals x. What's his name? I think I heard it. Starts with an I. Oh, I didn't hear it. No? It's something that our generation, your generation really struggles with? What they find their blank in? Ah. Identify. Uh-oh. Identity. Yeah, identify line. The identity function line, which is the same thing as the y equals x. Identity. I changed it. Identity. The identity function, y equals x. And something that you probably want to make a note of is the reason why it reflects across this line is because every single point on this side, x is A, y is B, changes to this corresponding point on the other side because the x and y switches. Oh, that's right. And graphically, how does that make a difference? Well, what's on one side of the y equals x goes to the other side. Now, these can get kind of tricky. Just a heads up for those of you that were working on homework, you might have seen. Sometimes these get tricky, so just maybe like a quick little sketching piece of advice. If you have one function and you're trying to reflect it across the y equals x line, like it's not always so easy. So what I would think of if I were you, if you were trying to reflect, is take it piece by piece. So for instance, this guy is a swoop. Away from the line, okay, I need to swoop it away from the line on this side. This guy is right next to the line, almost parallel, okay, right next to the line, almost parallel. Then he bulges out, all right, fine, bulge out, all the way until he hits the line. Okay, cool. And then switch that little tail piece to the other side of the line. It's just a piece of sketching advice. Take it piece by piece, otherwise it gets kind of messy. And I think in homework I gave you at least one tricky one. Yeah. My door's closed, which means I am not triggering the air in any way, shape, or form. And there's a lock on a box that I'm not allowed to touch. I know. I'm sorry. It's locked. Go ask Mr. Leverton. I don't know why. I think it's actually just to save on energy costs because if teachers are always like beep, 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 beep all day long, then it messes. Anyway, that's the ultimate reason why. Hey kiddos, you don't actually need to write this down unless you really, really want to. I know Jordan, Bill's character, hang in there. It's killing all the germs that are flying around our school because people are getting sick. For preserving them. For preserving what's already in here, but you guys joined the environment. Coming back. If you were supposed to check graphically that these two are inverses, guys, is it enough just to stare at it and be like, nah, I think it looks good. Yeah, it kind of folds. What could you sketch in your graphing calculator to make sure that they actually are reflecting across the y equals x line? Yeah. Why not, if you get a question like this and it's asking you to graphically check, why not graph y equals x? And if you graph y equals x, guess what? You're going to see, yep, one side, the other, one side, the other. Sometimes, like with the zoom, it gets a little skewed and it might get a little confusing. But if you graph y equals x, it's just going to help out a little more. Could you also switch x and y and check it that way? Of course you could, but that was just a quick piece of advice. If you're supposed to look at a graph and put it in your graphing calculator, maybe graphing y equals x works. Oh my goodness, we already talked about this one. I bet you guys can fill in the blank on your own. All right, I was checking the temperature setting. It's a little lower than it usually is, so I'll go ahead and email Filberto. And I'll say please. But get this page down. Oh, you guys already filled in the blank, didn't you? What's the blank? Switch. There we go. That's what I was looking for. Was it this cold yesterday? It wasn't, was it? Okay. No, it's not that spiffy. Walk in here, grab his nifty key, unlock it, and then they have it programmed, but it's not like to an app or anything that you can. Yeah, but you mean on campus? Higher. There's a nursery that meets in here on Sundays, Mr. Carmichael's church, and so the box is off on Sundays so they can play with it for the kids because you can't have little kids in like 70 whatever. It's 71 degrees. Like that sounds nice, right? But I know you guys are cold. Yeah. Well, the thermostat is set to 71. The thermometer actually shows it as like 68 because it turns on and then it stays on too long. Anyway, without going into tons of detail. I think on Sundays when the nursery's in here, it messes up the programming, so they have to come in and redo it again. Yeah. Come up, you'll see the little red line. Just don't break it. Anyway, coming back. I'm not sure if it's mercury, but either way, don't break it. Switch. Guys, this is an easy concept, right? Yeah. You guys see all the point switching? And graphically, how does that? Graphically, how does that affect the graphs? That's awkward. Sorry. How does it affect the function? It's that fold over the y equals x line. So you can just take it point by point, kind of like we did transformations in section 1.7 with translations, dilations, reflections, and we took it by points, or you could take that whole function and actually do that reflection. Okay, here's the second important thing for today. Solving for F inverse, done, practiced, except for a couple tricky ones. Maybe we'll try to do one before the end. But here's the second big idea. What does it mean to be invertible or one-to-one? Yes, just in case you're curious of the language, the English, this is an adjective describing functions. It's an adjective for functions. Huh? One-to-one. Just another way of saying one-to-one. Each x has only one y and each y has only one x. So it's one-to-one in the sense of going forwards and backwards. Whereas normally for functions, we only need each x to have one y. We don't need it to go the other way. But to be an invertible function, it's not just going to, turned off. It's not just going to pass the vertical line test. It's also going to pass the, think, everything switches. The x and the y's switch. The graph reflects over the y equals x line. So the vertical becomes the horizontal. Vertical line test. Vertical line test, each x paired with one and only one y, that's to make a function. Horizontal line test, that's to make it invertible. Yeah, because here's what's going on. I was trying to kind of lead into that. If original functions pass the horizontal line test, when you flip them, the inverse is going to pass the vertical line test. So to be invertible, a function's inverse has to also be a function. But for the inverse to be a function, for the inverse to pass the vertical line test, you guys need, or we need, the original to pass the horizontal line test. For the inverse to pass the VLT, or the vertical line test, for the inverse to be a function, the original has to pass the horizontal line test. We can also call that one, like we do with vertical line test, the HLT. VLT, HLT. Yeah, sure. A quadratic is never going to be, what's the word? Invertible. Never going to be one-to-one. So a quadratic. Why never, never, never? Because every quadratic, just by definition or by, I don't know, description of it being a parabola, is going to fail the horizontal line test, right? So if I was to put your y equals x squared, f of x equals x squared, if I was to graph him, is this a function? Yes or no? Oh, I know. This gets confusing. Is this a function? Yeah, because it passes what? Okay, so I could call this f of x. He's a function. He's fine. But what's going to happen if you reflect him across? But why?
Because like this has like more than one point.
You guys see what would happen? This little piece going away is going to have a little piece going away. This little piece going, swoop, there it is, swoop, there it is. And then this little piece going away again. Oh, it's going to go away again. What's true about this inverse? What does it fail? And how can we, well, the inverse, right? The inverse fails the vertical line test. The inverse is not a function. And how could we have seen that in the original? The original fails the horizontal line test. So that's what's going on. It's saying you don't necessarily have to get a graph every single time. Thank you. I don't know why it reverted. But the original passed the vertical line test. He's a function, but he fails the horizontal, which means when you go to reflect, the inverse is going to fail. Now, here's the tricky thing. This is one way to figure out invertible, but the problem is you need to know what the graph looks like. And can we go back to homework real quick? Do you guys know what all of these graphs look like? Some of them, right? But do you know all of them? Okay, well, we don't want to just be stuck to needing a graphing calculator or doing a table. So is there any other way to figure out invertible without just looking at a graph and seeing whether the original passes the horizontal line test? The answer is yes, but first, let's say, okay, what if they do give us a graph? Which of these are invertible or one-to-one? Thank you, Jose. Do you guys say thank you?
Thank you.
Which ones are invertible? First one is? Okay, first one is one-to-one or invertible, check. Second one is not. Oh, okay, good. That one fails. It's a quadratic, right? Totally fails the horizontal line test. Each y is not paired with only one x. That one, doesn't it pass? Okay. So that one's one-to-one invertible. That one's not invertible. Why is this one invertible? Pause. That's the definition of function. It's a function, true, but is it an invertible function? Doesn't each y need to be paired with only one x? You have to think backwards now. So it's a function, yes. Joe's saying, I think he can read this. It is an x squared, so it's going to fail. But if you look at the table, how can you tell it's going to fail? The 4 goes to more than one x, right? The 1 goes to more than one x. So if there's a y that maps to more than one x, that's going to fail being invertible. So invertible, or short way of saying one-to-one, nope, fails. Yeah. Never. Never, never. Now, this is what I was talking about a second ago, though. What if the spacing is awful, and I need to go fix that for my OCD ones. But besides the spacing, question, do we really want to have to figure out the graphs to both of these to answer the whole one-to-one thing? And the answer is, hopefully, no. Hopefully, no. Now, pause really quickly. Why are you guys laughing? You're not helping me keep a straight face. So, letter A. Question. He's getting it out. What is this guy? It's a squared. What kind of function? It's a parabola that's been shifted. Come on, shifted. Inside, inside. Unexpected. Okay, good. 2 to the right. Whew, got there. Yeah, it's inside, right? So it's a parabola that's been shifted 2 to the right. But either way, it's a parabola. What does every parabola fail? Okay, so we can say right now that he's not one-to-one. Nope, he's not invertible. Letter B says still solve for the inverse, though. Now, technically, I suppose you could be like, I shouldn't have to do that because the inverse function doesn't exist. But does an inverse still exist? Yes, he's just not a function. So how would we solve for the inverse? Good, make f of x, y, and then switch. Is it okay if I just go straight to here? You guys tracking? Okay. How can we see this is not one-to-one without thinking of the graph? Because in a second, we don't want to think about the graph because we're like, I don't know his graph for number 2. Okay. Well, algebraically, how can we figure out that his inverse won't be a function? What are we supposed to do after we switch x and y? Simplify by solving for y. How do we solve for y? Take the square root to undo the squared. What did we learn yesterday about what happens when you square root a squared? And leaves behind the absolute value. So what's the struggle when we have an absolute value? How do you get to y? 2 different equations. Oh, so to make the inverse of this guy, there's going to be 2 different functions? It's impossible for non-invertible functions. It's impossible to write the inverse as 1 function. It's always going to be a combination of 2. Because if you were to flip this parabola, when we go this way, it's not a function, but you can redefine him, and you can talk about him in terms of, oh, hey, a positive square root function, radical function, remember the parent function graph? And a negative square root function. We can talk about him in terms of 2 separate functions. So here's the idea. Can I say f inverse of x equals both of these? No. But can't I say this is basically an inverse relation, right? This is the inverse, I just can't write that function notation. So in some ways you could say the inverse function does not exist. The inverse function does not. But 2 inverse functions put together, in essence, would do the job. Now letter C says verify. Do you guys remember how we would verify that these functions are true inverses? Plug in and one better be the undoing of the other, right? Okay. Well, let's do a dot, 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 because we practiced that today already. Let's go over to this guy whose graph we don't know. And so I can't even think about the horizontal line test because I don't know what he looks like. So we'll come back to the one-to-one and we'll say, wait a minute, but we just saw something funny happen when we were solving that gave us a clue as to why it failed being one-to-one or failed being invertible. So let's talk about this guy. How do we solve for his inverse? Are you guys okay if I say x equals 5 minus y over 2y plus 1? Check it. Are we good? Cool. Ready, set, collaborate in your groups to try to get y by itself. Go. Can you get y by itself? First thing to do is multiply. Great idea. This is really tricky for a lot of people. But I did just steal what Jason said. First thing to do is multiply. He's right. Play with it. Careful. Technically not the word. Foil isn't the word. But the idea is right. That's what you're saying. Yeah, check each other. This one's hard. But think through the multiply clue. All right, turn behind. See if you guys can work together. Maybe 3 brains better than 2. You guys got it yet? Wesley's checking in with you, Priscilla. Any ideas? Did you figure out the right word yet? Not but distribute. Multiply and then distribute? Perfect. Did you do it? Multiply and then distribute? I know it doesn't look right, huh? Try it, try it. It's not going to look right. Multiply and then distribute? Anybody figure out the next step? Move the y stuff on one side and the non-y stuff on another side? Put the y terms on one side, put the non-y terms on the other side? Factor? My turn. It does have an inverse. Multiply, distribute, put the y terms on one side, the non-y terms on the other side, factor.
Wait, why don't you just move the x to the left side and then it becomes like x plus y squared? Yeah.
Move the x to the other side.
Yeah, just plus x to both sides in the...
But that doesn't get y by itself.
No, the one.
That doesn't get y by itself.
It doesn't get y by itself, but it can get a square and then...
But we have to get y by itself.
Okay, that's what I did.
Dun, 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 dun. Jordan, it's like your weird 1 over x1. It is its own inverse. How would you verify? Plug one into the other. It works? Oh, it totally works. It's just disgusting. But it is its own undoing. And here's the question. Is there a plus or minus that happened? Is there more than one function that was a part of this inverse? No. So is it invertible? Yes. If you graphed it, would it look invertible? Yep. Why? Because it would pass the horizontal line test if you were to use your graphing calculator. Whoo! Ponder it. It's okay. Play with your homework tonight if you have one. Every now and then a function is its own inverse. Maybe tomorrow we'll look and verify and make sure it really works, but I promise you it does if you were to plug one into the other. Homework number 9, section 1.9. We got to go over a tricky one here at the very, restrict the domain. Restrict the domain. What's it talking about? Graphing it really helps because on this one, it's an absolute value that's been shifted. Yeah. You could find the 0 of this function to figure out where it hits the axis. This one ends up just having horizontal translation and a bit of a horizontal stretch. We end up with x equals -1/2, which tells us where the v hits if we were to actually break this guy down into its transformations. Here's the dealio. Does he pass the horizontal line test?
Yes. No.
No, he fails. He's a function, but he fails being invertible. But then they say, wait a minute, make it 1-to-1? Here's the idea. This guy's domain right now is x, how left, how right. X is all real numbers. And the range, y is how low, how high. All the positive numbers, including 0. When we go to our inverse, what we need for our inverse is we need our range. Well, hold on. How does this work? For the inverse function, it doesn't naturally have a function, or it doesn't naturally have an inverse unless we restrict. What we need is still everything from 0 to infinity, but we need to ignore the part of the graph that makes it fail. So for the inverse, instead of just switching the domain and range, because it doesn't work, because it's not invertible, what we're going to do is consider the graph and say, oh, I need to take away part of the graph to restrict the domain to be able to make it pass. And so what we're going to do is, instead of having all real numbers, we're going to say, no, 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 that doesn't work because it fails. Go from -1/2 to infinity. Now we can go ahead and do our domain and range by switching. All right, cool kids. I'll let you get out of here. This will be saved online in the notes in the YouTube if you need to come back for homework. Bye, guys. Bye. There we go. Forgot that homework helped.